thanks for the organizers for the invitation to this really nice conference, and I've really enjoyed my time here. So we'll talk about geodesic Levy flights and something called the Foraging Hypothesis. And this is joint work with my postdoc, my graduate student, and my own brother, so it's family business. And also joint work, the second part of this is joint work with my friends at CNRS, Monte, Chauvet, and Levy. All right. So I will start with a very simple problem, and this is where the root of the problem came from. So suppose now I have a particle in a bounded region, and that is undergoing some Brownian motion. And the boundary is set up in such a way that if your Brownian particle were to hit that boundary, it's just going to reflect, and it's going to keep on going, right? And it's continuous forever. Now suppose I cut a little hole with epsilon along that boundary. And what happens then is that if that Brownian process hits that little hole, it's going to escape through that hole, and your Brownian process just dies, right? So that stops. So the question is, well, what is the expected time it takes for this particle to escape through this little hole? And in particular, people were very interested in what happens as epsilon goes to 0, right? So imagine if the hole becomes smaller and smaller, it gets harder and harder to escape, and therefore it takes longer and longer time. So people were interested in what is the asymptotic of the escape time as epsilon goes to 0. Is it like a polynomial growth, or is it like an exponential growth? And it turned out that this problem has a very physics-based root. So the first work on this is done by a bunch of physicists. And it turns out that in dimension 2, it blows up like log epsilon. And in dimension 3 and higher, it blows up like epsilon to the minus n plus 2. And if you remember your PDE class, the Green's function in dimension 2 is the logarithm of absolute value of x, whereas in dimension 3 and higher, it's absolute value to the minus n plus 2. So there is a Green's function lurking in here somewhere, and there's definitely where harmonic analysis is going to show up. Right, so the problem that I'm going to consider is going to be slightly different. Right, so I want you to imagine that you're on a desert and there's food. And there are two animals that are going to try to find this food. One animal takes the strategy of going about in a random but continuous manner until it finds its food, and of course it stops, right? The process stops. The second animal also wanders around randomly, but is allowed to take long jumps, right? So these are called Levy flights until it finds its food and it stops. And of course, the most natural question is, well, who is expected to find their target faster, right? So it's advantageous to do that. And in fact, there is something called the Levy flight foraging hypothesis in the field of biology that says that a lot of animals have evolved to take on Levy flight as its foraging strategy because it is actually advantageous, right, through natural selection. And if biology is not your favorite subject, and you care more about something like data science, there are actually computational algorithms that are based on these animal foraging strategy, and these are called bio-inspired computational algorithms. So on the left, there is a search algorithm that's based on Brownian motion. On the right, there is one on Levy flight. It's even got nice names like the gray wolf optimizer. Right. So these problems have mostly been studied in flat Euclidean space. And the story that I will tell you is what happens when we introduce curvature into this problem, and what additional features that you would see that you would not otherwise see when in flat space. All right, so what new things do we discover when we introduce curvature? And so there's a good reason other than mathematical curiosity to think about these kind of problems in curved spaces. For example, animal foraging behavior is dictated by terrain, and terrain is of course curved rather than flat. And if optimization, again, these computational algorithms is more your thing, there are actually various optimization algorithms that are constrained optimization algorithms where you're looking for the minimum, not globally, but you're constrained to some manifold, right? So this is, again, a very good reason for wanting to look at these kind of problems on curved spaces. All right, so really the problem that I'm interested in is now I'm on a curved surface and I have either a Brownian motion or some kind of a Levy flight, which I will describe later, and it will go about on this, say, curved surface until it finds its food or finds that target, and it stops. And I'm interested in what is the expected time for this to happen. Right, so let's look at the results that I have for Brownian motion on the sphere. So let me sort of describe to you what kind of Levy, how to describe these Levy processes. Right, so the Brownian motion on a curved manifold is very much just like Brownian motion on flat space, because after all, any smooth manifold is approximated to the first order by just something flat. Right, and at every increment, I just take an infinitesimal step in each direction, so I don't really see the global geometry too much. Right, whereas the geodesic Levy flights, however, they behave in this way. So suppose I'm at this point, I will randomly choose a unit direction in any that's given uniform probability, and then I will take a geodesic flight along that direction the length of that step that I take is given by the power law, right? So it's the length is given the probability distribution L to the -1 -2 alpha, all right? Where alpha is a parameter that determines the likelihood of long jumps. And then I will choose a random direction again, I will jump, and I'll choose a random direction again, I will jump. And so that will be my Levy process, my stochastic process. So the length of the jump is given by this distribution, and as you can see, if alpha is very small, it is very likely to take long flights, where if you take alpha to be very large, it's very unlikely to take long flights. You're mostly just doing Brownian motions. All right, so the important thing here is to realize that this differs very much from the Brownian motion case, because at any given increment, I could have very unlucky, and I sampled a very long jump, and I could just wrap around this torus a million times, and therefore each jump depends on the global geometry of my manifold, right? So this is where the global geometry really shows up in these stochastic processes. All right, so now the question that I'm interested in is the expected time for finding a small target. So that red spot there is the target, and it's a target is a geodesic ball of radius epsilon centered around some point P0. And I'm interested in what happens as epsilon, and I will call U epsilon P to be the expected time of finding a target of size epsilon, given that the process starts at the point P, right? So this is now a function of my starting point. And so what I'm interested in is the behavior of this function, U epsilon P, as epsilon shrinks to a point.
Excuse me, the central point of the target is fixed?
Yeah, the center of the target, you could actually, it's an interesting problem when that target gets to move, right? That's a different problem.
Okay.
So let's see what results we get. So on Brownian motion, the expected time for finding this target up to leading order is independent of P, first of all. Up to leading order is independent of P. All the P dependents are in these lower order terms. In dimension 2, again, it's a logarithm of epsilon as epsilon goes to 0. And as higher dimensions, epsilon to the power -n+2. So again, these sort of Green's function-ish kind of things start to show up. And this is joint work with my graduate student, Trad Nursatanov, and my brother and myself. Now for Levy flight, however, the leading order blow up as epsilon goes to 0, it blows up like epsilon to the -n+2 alpha, plus some lower order terms. And unfortunately, we're only able to do this when the manifold is quite special, right? So it needs to be either the perfectly round sphere, or the flat torus, or a negative curvature. All right, and you'll see why we can only do these soon. Of course, the negative curvature is the interesting manifold here, because this is not the sort of something that you can explicitly write things down. Right, so remember that alpha here is a parameter which describes the likelihood of long jumps. So this is joint work with Bontonneau, Chauvet, and Lefebvre. All right, so if you look at these numbers carefully, right? So if in Brownian motion case, it blows up like minus n plus 2. And in the Levy flight case, it blows up like minus n plus 2 alpha, where alpha is strictly between 0 and 1. So Levy flight actually blows up faster, right? So it takes longer time to find your target via Levy flight. And this seems to agree with some recent results by some biologists where they used intuition and to sort of argue why, in one dimension at least, Levy flight is not advantageous, right? You much rather use Brownian motion when your target is small. And so this is consistent with what biologists are thinking about.
You talk about the time to find your target. Do jumps take time proportional to their length, or is it unit time?
It's instantaneous, regardless of length of the jump.
So time is number of steps.
No. So this is something I swept under the rug a little bit, right? So after each jump, you actually wait a certain amount of time that's given by an exponential distribution, which depends on alpha. This is how Levy processes work.
Yeah, I see.
And I'm not sure, again, like you can argue whether or not that's a good model for any biological process. That's another discussion.
So, do you see the target when you fly?
No, you don't see the target, right? So this is the blind search. Right, so that you can overshoot. And this is exactly what they're arguing here in this paper. If you read this paper, they say, well, if your target is small, there's very large likelihood you're going to overshoot that target. Therefore, it's probably not too efficient to take these jumps. Right? That's what their argument was.
Maybe you could say that this Levy kind is the pure jump situation, and you can also make jumps plus a Brownian motion between jumps. And in that case, mostly the Brownian motion dominates.
Yes,
And
right.
You don't see the jumps, basically, for it.
Right. But in our case, it's pure jump. All right, so now we also did Monte Carlo simulations for, of course, it's stochastic, so you can do numerical experiments. So we did Monte Carlo simulations. In a special case where manifold is the flat torus. All right, so this is our little algorithm. So we split our grid, torus into small grids of size h, and then with that grid size h, I need to have a time scale that respects that grid size. So this is where the time and space are correlated. And so now, given your process at the end step, right, you sample a vector given by that distribution, of an integer vector in that distribution, and then you take your next step to be xn plus h times that vector that you sample. All right, and of course then you take mod 1 because you want to stay on the torus. And so now, and then elapsed time is equal to elapsed time plus this time scale, h to the 2 alpha, right? And then you sort of go on, and repeat until you land on the red target. Right, and some work that would show that this discrete process would actually converge to your continuum process that I described earlier. All right, so now this is our Monte Carlo experiment. We have a target at the center of our torus, and we start our process at the lower left corner, 0, 1, 0, 1. Right, and we're interested in what happens. We're computing various Monte Carlo simulations as this target becomes smaller and smaller. All right, so this is our result. Right, so the blue curve is what we compute. We theoretically prove that asymptotically it must go along this blue curve, and our numerical Monte Carlo experiments are these crosses. So as you can see, as epsilon goes to 0, the experiments start to get closer and closer to my theoretical prediction. All right. So we also, not only did we compute the expected stopping time, we actually gave the full distribution of the stopping time, right? So remember that alpha controls the likelihood of long jumps, right? So if alpha is large, you have long jumps very unlikely. Small alpha, you have very likely to have long jumps. So if you're very unlikely to have long jumps, you will see that most of your processes finds the target in a relatively small amount of time. Right, and there's sort of very few stragglers. Whereas if you're allowing yourself long jumps, very few processes actually find your target in a short amount of time, and it's almost like a uniform distribution. You're equally likely to find the target at any given point in time. All right, so now this is where so far no geometry has come into play yet, right? So there's sort of no difference in my result whether or not it's the flat torus, the round sphere, or the negative curvature. But now this is where geometry really starts to play a role. So if I want to look at the spatial average of my expected stopping time, right? So U epsilon p is the expected stopping time given that you start at the point P. And then if you want to average over all possible starting points, that is the average, the spatial average, which is U bar epsilon. And because you have a good asymptotic for U epsilon at each given point, of course you have a asymptotic expansion for the average just by simply integrating. Right? And so what you want to look at is you want to look at the point-wise deviation of your spatial, of your U epsilon p against the spatial average. So this sort of tells you how special a starting point is, right? If a special point, if epsilon goes to 0 and the U epsilon p sort of never really deviates too much from U bar epsilon, it means that that starting point is not so special at all. It sort of behaves in an average way, right? And indeed, that is the case. No point is special on the torus, and that's what you expect, yeah? Or has negative curvature. So in both of these cases, the spatial average does not deviate too far from the process starting at each point as epsilon goes to 0. On the sphere, however, as the target shrinks down to a point centered at some p0, if your starting point is not the antipodal point of your center of your target, then those points are not so special either. They don't deviate so much from the average as epsilon goes to 0. However, if you start at the antipodal point of the center of that target, you start to deviate a lot as epsilon goes to 0. And that is, of course, those two are conjugate points, right? So the conjugate points start to play a role in your stochastic process. Now this is where geometry and your probability process actually starts to interplay with each other. All right, so this kind of foreshadows some of the propagation phenomenon that happens when you have conjugate points rather than when you don't have a conjugate point, right? So this is sort of, we'll get into this a little bit later. All right, so this Fourier integral operators actually plays a role in this. All right, so now in order to get into
in the case where we start at the antipodal point, do you know if we are expecting to reach the target more quickly or in more time than an average?
I remember it depends on the sign of this thing going to infinity, right? And I recall that when we computed, if we didn't make any errors in sign, I think this was going to minus infinity. So it's faster. And because there is a chance, right? Because no matter which direction you choose, if you jump length pi, you would always land up in there, right? So there's sort of a more likelihood of being able to jump to the target if you start here in one single jump. So that's sort of the intuition. All right, so now to get into the whys, right, I need to start talking about infinitesimal generators of stochastic processes. And so let me sort of, give you remind you what these things are. Yes. All right, so now if I have a Brownian process, x of t, and I have an open set B, and I would like to know what is the probability at time t my process is in this open set, given that I started at the point P, right? And so this is given by a probability density distribution, right? U of t, which tells you what, keeps track of what time it is, right? And P keeps track of where you started, and Q is your dummy variable for integration. And you integrate over the set B. And so what is this probability density distribution U? Well, so let's suppose I put 100 particles all at this point at time equal to 0, and I turn on and I let them undergo Brownian motion, right? So at the beginning, this doesn't pause. So at the beginning, you would see that the distribution was a delta function. That was because I had 100% certainty that everything was in at that point to begin with. And as time starts to go, you know, it starts to diffuse and my standard deviation gets larger and larger, right? So, of course, this is very classical, is that your probability density function is given by the heat equation. It's the fundamental solution to the heat equation, right? So you solve the heat equation with initial condition being the delta function at your starting point. And so this is very classical, right? So infinitesimal generators are, the infinitesimal generator of Brownian motions, of course, is the Laplace operator, right? So this is classical stuff. And so once you have the infinitesimal generator, you have a very good way of actually calculating your stopping time, because it's an easy computation to say that the expected stopping time, given that your process starts at p, so that is a function of p, and this function of p satisfies this Laplace's equation. Laplace of this function is equal to -1. So really, if you want to compute that thing, all you really need to do is be able to invert Laplacian given some kind of a boundary condition here. Right? And that's very elementary. And so you invert the Laplacian, and just remember that the Green's function of the Laplacian is the power minus n plus 2 in, say, n higher than or equal to 3. So that exactly corresponds to the epsilon to the -2 plus, at minus n plus 2, right? So that's where the Green's function comes in. Levy flight, however, is a little bit trickier, right? So if you still look at the same question, at time t, what is the probability of my process is in a open set B, given that my process started at P? It is also given by probability density distribution. And this probability density distribution also satisfies some kind of a heat equation, right? It's some time derivative with respect to T is equal to some operator A applied to U with the initial condition that is the delta function at the starting point. But this A here could be very strange depending on your geometry, right? So A is the fractional Laplacian if M is either the flat torus or Rn. This is very classical. People knew this a long time ago, that the infinitesimal generator for Levy flights in Euclidean space is the fractional Laplacian. But turned out that is not the fractional Laplacian in general. Right, so it is actually in the year 2000, Applebaum and Estrade, they actually worked out a precise formula for what this infinitesimal generator is. So it is, you take, if you want to compute A at a point, AF at a given point, you integrate F composed with the exponential map for all time, and then you average it over all possible, over the sphere bundle, over this fiber, over that point. Right, so as you can see, there's sort of no easy way to deduce any useful properties from this formula, at least in the year 2000, right? So what are its spectral properties? Is this operator invertible? In the case when you have the perfect round sphere or you have the flat torus, of course you can write down explicit formulas for your geodesic flow or the exponential map, and you can do this by explicit computation. Otherwise, little can be said. Until, of course, the work of people like Maciej and Dyatlov and with Sjöstrand and Guillermo gives us some way to understand what it means to integrate over geodesics and what is the resulting object that comes out of this operator, right? So this is where sort of the new machinery gets applied to this old problem. All right, so what we showed was that A is actually a Fredholm operator with non-negative discrete spectrum. And the expected stopping time also satisfies now this kind of elliptic exterior value problem. And so therefore you can compute the expected stopping time just simply by inverting A using Fredholm machinery. All right, so let me tell you a little bit about this infinitesimal operator on various geometric objects. So first on the round sphere, or first on the flat torus and the round sphere, and then negatively curved manifolds. So AF is this operator here. You first compose F with the exponential map, integrate over all time, average over the sphere, or the unit sphere. Right, so what you do is you if you want to compute A at this point, you choose a direction V, you integrate over that entire direction, over the entire geodesic in that direction, and then you integrate over all possible geodesics coming out of that point. All right, so now for the flat torus, of course, the exponential map is very easy to write down. It's just P plus T times the vector that you have chosen, right? An explicit calculation, that's just the fractional Laplacian. It's nothing new there. All right, so now on the sphere, that is where things get a little bit more interesting because you got conjugate points, right? If you want to compute AF of P at this point, that's your point P, you look at all the possible geodesics emanating from that point. Of course, they all focus also at the antipodal point. So there are two different places where these geodesics focus. One is where the geodesics came from, the other one is at the South Pole, right? And so this gives you two singularities to this integral kernel. One is where your kernel is singular, you're dividing by 0 when P is exactly equal to Q, and that corresponds to this point where everybody focused. And there's another focal point at the antipodal point, and that would give you another singularity where you're dividing by 0 when P is the antipodal point of Q. All right, so now let's look at these two integrals, these two operators, and see how differently they behave. Right, so the first operator looks like the Green's function, right? Because it is similar. Because you're dividing by 0 exactly when P is equal to Q, and the Green's function, you're dividing by 0 when P is equal to Q. The power is a little bit different, but the geometric structure is roughly the same. Right? So what does this operator do? Well, so suppose I take the delta function being f, and I stick it into this operator. The resulting operator is this thing that you sort of spread delta function out a little bit. Now, these two things it may look like it has changed this delta function by a lot, but one thing you observe is that the singularity is at 0, and the singularity still stays at 0. So this thing does not move singularities in any way. Right, so this is apologies to my fellow microlocal analysts for explaining this. So one thing you notice is that the Green's function keeps singularities in place. Now the blue operator here acts more like a wave function in some way, or the wave operator in some way. So how does it act like the wave operator? So if I want to solve the wave equation, and I start with some kind of initial condition f of p. So here's my initial condition f of p, where it's 0 on the left and 1 on the right, right? And I start propagating this wave, and that is just simply going to shift to the right, yeah? And so at any given time, the solution is given by this integral applied to the initial condition f, right? So now you observe at time is equal to 0, I had my singularity right here, but at time as another time, the singularity got propagated. And this operator, despite the fact that it looks quite different from this, you've noticed that also the singularity for this operator is not at when p is equal to q, but rather when p is not equal to q. All right? So in some sense, this operator here propagates singularities. Right, and this is something called a Fourier integral operator. And one of the properties, or the main properties of these things, that it propagates singularities. And in our case, this is the sphere case, right? If P is a singularity of F, then the antipodal point of P is a singularity of AF. And so recall earlier that we had this property here, where if your starting point is at the antipodal point of the center of your or the center of your target, which is a singularity because that's a sinc, that singularity gets propagated to the minus to its antipodal point, and that explains this spatial deviation that you see right here. Right, so you can see that this illustrates the fact that this point-wise deviation blowing up is a consequence of the propagation of singularity of Fourier integral operators. Now, how much time do I have? So I have still 20.
Yes.
So 20 minutes, right? So, and of course, the negatively curved case is the mathematically most challenging part. right? So here, so AF is given by the integral over, so you choose a unit vector, you integrate it over the exponential map given by that vector, and then you average over all possible directions. So what you do is you chop up this integral into two parts. You first integrate from some 0 to some within the radius of injectivity, which I call 1, just for simplicity, and then there's that rest of that geodesic. So in this, within the injectivity radius, of course, that's an easy computation, right? So this is just using boundary normal coordinate, or sorry, not just Riemann normal coordinates. You're able to show that that's actually nothing more than, or very close to just the fractional function, plus the rest of the geodesic, and that's the hard part, right? So you need to show somehow that the rest of this geodesic, or integrating f over the rest of this geodesic, always gives you something smooth, regardless of what f you put in, right? So that's going to be the hard part, and this is where and Lefebvre really helped me out. All right, so this is also this is where I use negative curvature. So now let me write this exponential map in terms of the geodesic flow, right? So the exponential map is nothing more than you take the geodesic flow and you compose it with a projection map. And so I want to analyze, fix a vector v, fix a direction first. I want to analyze what it means to integrate a function along the entire geodesic first. And in particular, I want to ask myself, what happens to the singularity of this f when I integrate along this geodesic? So the singularity of a function u on any manifold is encoded in something called the wavefront set, and this is, previous speakers have talked about this, and for me, I just sort of give you a more geometric intuition, is that if you have a function that's 1 here and 0 here, the wavefront set is just that conormal set that would indicate where the jump is. Right, so that's a subset of the cotangent bundle, and so this motivates me to consider, instead of just the geodesic flow, I look at the symplectic lift of that flow. And it turns out that if I were to take a function or even a distribution f and I compose it with a geodesic flow, the wavefront set of that function gets propagated by the symplectic lift. All right, so this is why I need to consider this lift. And so when MG has negative curvature, of course, this has this splitting where you have ES is your source, and everything gets propagated towards that, or your trajectory moves towards that sink. And so, right, so now I'm going to write this integral here into multiple operations, which it's just a calligraphy of just a different way of writing it. So I take f, I pull it back by the canonical projection, and then I pull it back by the flow, I integrate over it, and then I push forward by the canonical projection. So I'm going to tell you what each of these steps does to the wavefront sets of f. All right, so now let f start as a distribution on my base manifold. And so when I take f and I pull it back up by the canonical projection, that actually becomes a function that is constant along each fiber, right? So that's the pullback of a function that's defined on a manifold downstairs. And so for that, the wavefront set of this pullback, this is not any distribution on Sn, but it's the pullback of something that lives only on the base manifold. So its wavefront set is actually only restricted to a bundle, which is the perpendicular bundle to the kernel of the canonical projection map, right? So it's perpendicular to the vertical bundle. And so the wavefront set is contained only on this V star. And now when you start to compose f with the flow of the geodesic, is going to, because the flow goes towards the sink, it's actually going to push everything towards that sink. All right, so it's going to get pushed away from that co-vertical bundle there.
No, really, I mean, the point E0 star is not going to move.
Sorry?
The point E0 star is not going to move. Like
Oh,
you,
right, so this
should
actually
be
stays
bended.
here.
Like you should, you should
Yeah,
have
yeah,
something
I should have
bended
written it
towards-
right. Yeah, so that actually, so I should draw this wrong, so this should actually have stayed there. So now when I integrate, so when I integrate, of course, this doesn't change too much. And then now when I push forward, that only cares about the singularity on that, of the wavefront set on that co-vertical bundle. And because I don't see anything there, other than, as people point out, there's very little bit there that I actually need to deal with, but that's a technicality. Right, so it actually becomes something smooth. All right, so I end up getting a smooth object regardless of whatever I throw into this integral there. All right, so therefore, AF is the fractional Laplacian plus something that is smoothing. Right, so therefore, I have Fredholm properties for this. All right, so this is a theorem of Bolton-Chabet and myself. Is if my manifold is negatively curved, or if it's Anosov, then A is a pseudo-differential operator whose principal symbol is the same as that of the fractional Laplacian.
And what is C?
Oh, C is just the constant. It's just some constant. All right, so now I'm going to sort of talk about works that I think would be interesting to do. Right. So recall that on the round sphere, the infinitesimal generator has two parts. Right, so one has a singularity on the diagonal, the other one has singularity to the conjugate point. So that led to the fact that on the pointwise deviation, you have that if P0 is the center of the trap, then if you start your process at the antipodal point, then it blows up. The pointwise deviation blows up. And
How much does it blow up? I mean,
sorry?
How does it blow up?
How does it blow up? Yeah, it blows up to one order lower than the blow up of U bar epsilon itself, if I remember correctly. All right, so now this is probably true with the right assumption, is that if P0 on any arbitrary manifold be the center of the trap, then if you start your process at a conjugate point, I would guess that, the spatial deviation also blows up as well. All right, so there's another possible interesting direction for this is if you look at instead of geodesic flow, you look at billiard flow, right? So recall that our Levy process is given by if you start at a point, you choose a random direction, and you flow that, and then you jump a distance given by a power law distribution. So instead, we replace geodesics by billiards. You start at a given point, you choose a random direction, and then you just shoot your billiard, get the length given by that power law distribution, and so on and so on. So the question is the infinitesimal generator still given by the integral of the exponential map, right? Where this exponential map is now the billiard exponential map. And if it is, what kind of an operator is that, right? So is there sort of a notion of Anosov billiard where I can integrate along geodesics and still get something that's Fredholm? I don't know, right? So, and of course, this is one of these escape time problems, is that somehow if I have a small escape hole, what is the expected escape time as the escape window shrinks to a point, right? So that's another interesting question that would be interesting to look at. Yeah, and that's the end of my talk.
Questions? Comments?
So I have a question. So actually, it's to the thing that Yannick said about this. If you mix the two behaviors, so you have this jump process, and I don't know what alternates you give it, but you jump and then you make a little bit of Brownian motion and then jump again.
Yeah.
Is it so clear that the Brownian motion would dominate? I mean, wouldn't it kind of depend on how long you allow Brownian motion, or?
Yeah. So the process there goes by the following, right? So you start at a point, yeah, and then you immediately go to a Brownian motion, And the time that you do that Brownian motion is given by an exponential distribution, at which point you jump. And then you repeat this process, and then you go on a Brownian motion, and then you
So
jump.
you give them both the same, so the distribution that decides what happened, so when the next iteration happens is the same?
Yes, it's independent.
So, but what is if you give them different distributions? So to say, is it like, for example, an exponential distribution with a different rate?
Between the Brownian motion and the jump process. So the jump process and the Brownian motion are completely disjoint from each other, right? So the Brownian motion is the Brownian motion.
Yeah, no. I was just wondering if it were, which sort of, for the end time, so to say, for the expected time at the end, which asymptotic would dominate, so to say.
Oh, so the Brownian motion is given by the infinitesimal generator for the Brownian motion is Laplacian, right? And so that is the order 2 operator, whereas the jump process is given by roughly a fractional Laplacian. So it's like order 2 alpha, where alpha between 0 and 1. And so the dominating one is the Laplacian. So in some sense, the interesting case is when you have pure jump case, because then your leading order is this weird pseudo-differential operator or Fourier integral operator rather than just the Laplacian. Right? Because the leading order always dominates your behavior. So,
and this is true even if I give them different, so if the time, how long I have my Brownian motion and how long I have my jump process varies? Or is different, so to say? I mean, I'm just thinking about, like every time I start my Brownian motion, I only have it for extremely short time periods.
sorry?
Every time the time I do Brownian motion is extremely small with comparison to the jump process.
But you don't get to choose that. That's a random variable, how long you do your Brownian motion.
Okay, but you choose it according to an exponential distribution, right?
Yes, so you choose it according to exponential, and that exponential distribution is completely controlled by the parameter alpha you have chosen to begin with.
Okay, but I mean, this is maybe a bit off this topic, but I mean, I could imagine giving it a different distribution. So, like, to really have to, I mean, if they, I can understand what you said when which one would be dominant if they kind of have the same weight in time, but if I was wondering if, you know, the Brownian motion would be for much shorter time scales in comparison to the jump process, if there is some critical parameter where you would kind of see competition between the two.
Yeah, that would be interesting to look at, yeah. So, I don't know. I still think that the Laplacian would still dominate. I still think because your pseudo-differential or whatever pseudo-differential plus FIO is going to be your second order operator is always given by Laplacian and something lower order. And then when you try to invert that thing, you're inverting now it's just some elliptic pseudo-differential parametrics now, and that gets quite classical.
Okay. Can I ask a second question? Otherwise, I'll ask it later.
Go ahead.
We have time, so...
No, go ahead. There's time later.
Yes, so my question was about, what you need to know about the process is the long-time behavior of the process when epsilon goes to 0.
Yeah, the small target, yeah.
Small target, yes. So does the spectrum of the generator plays a role?
The spectral generator plays a role.
It's long time. Expect that. So heat equation for long time.
So in our proof, it doesn't show up.
The spectrum of the operator plays a role when you look at the time it takes for your probability distribution starting at a direct mass to evolve to become flat, essentially.
Equilibrium, yeah.
To the equilibrium state. That's what the spectrum governs, but it doesn't govern.
It governs what?
If you start with a direct mass and you let it evolve by your process, so it will evolve by the equation essentially. And then if you have a spectral gap in the spectrum, then this is how this is how you compute the time that it will take to get to the equilibrium state essentially. Yeah. But it's not really connected.
But another question is like, you look at this weird operator, can you give it a spectral gap control in terms of curvature, right? That's something that's quite classical for the Laplacian, but we don't know. And it's actually relevant, as you said, it somehow, it controls how quickly your system reaches an equilibrium, right?
The question.
So, well, common questions are having to do with your last two things. So with the billiards, maybe, I don't know, I was just chatting with Keith, you might have to work a little to find something that is actually uniformly hyperbolic. The classical ones, the Sinai billiards, are non-uniformly.
Right.
You will have to deal with singularities, but I don't know if the theory might help you, because they all have singularities, these billiards.
Yeah.
With the conjugate point things, have you tried the L.Tzou that has one of these loveliest conjugate sets?
No, we haven't. Yeah.
With cusps.
That would be a good first step.
You can, in principle, know what all the geodesics are, and you might be able to sort of check whether you sort of conjecture that you had
Yeah.
Well, this billiard had conjugate points, on the horizontal, and there are 2 points which are conjugate here for this one.
Computations for this fraction Laplace and where it appears on the FAO part and so on, they look very much like a computation of the normal operator for the geodesic X-ray transform. Well, there's no alpha there first, and then you integrate over a finite length, right? But I wonder what part of that can be used, because then the FO part appears if and only if they're conjugate points. And if they're not, this is kind of trivial that you can avoid it. So why isn't that the case here?
So I'm sure that's I'm sure that what you said is going forward. So this AF here, right? So there is this paper by Holman and Uman on the normal operator for when in the presence of conjugate points, right?
I did a paper by Gunther and me before that.
Oh, I'm sorry. There's also a paper by you and Gunther before that one, right? And my understanding is that you actually need to assume certain things about you are not allowed singular conjugate points in these.
Only if you want to do something more. Just to say it's a FA, okay, it is. But if you want actually to analyze it, invert it, whatever, then you have to worry more. But in 2 dimensions, there's no problem.
Oh, okay. So you know more than I do about that one.
The problem is that here you're integrating over infinite time, and that.
Right. Yeah. So in your case, you have boundary.
Boundary that you don't really see. You just escape. Once you escape, you don't come back. It's integrate over finite interval. Yeah, I understand.
Yeah, so that's something additional difficulty we have. Colin?
How do you deal with the infinite time? Because the wavefront set argument works for finite time, but at some point you need to do something for between, let's say, big time and infinity, right?
Right. How do you deal with this? Yeah, so let me see if I remember correctly. I think you use the fact that you actually, so something helps you here is that this is actually absolutely integrable, right? So you can actually take advantage of that. And so you don't actually necessarily get this infinity behavior that you would otherwise get if you don't have that t factor. And so you're actually dealing with convergent objects. And so that helps you.
So just my other question, do you think, so if you add a random environment to it, so you don't have, in a sense, a purely deterministic sphere where your random walk happens or where your Brownian motion happens, but you allow for some, I don't know, either small perturbations of the metric or obstacles appearing.
So I mean, you're allowing, say, like a time-dependent metric that's also stochastic in some way?
I mean, I was just wondering because I mean, while whoever searches for the red spot, in a sense, time goes on. I mean, the conditions can change. So I mean.
Yeah. So one thing is that the target can move as suggested. Right. The target can move in a Brownian motion. The center of the target can move, so you can look at like a moving target that's also shrinking, I guess. Right. So that's one way of having environment change. That's actually been done in applied math literature. Like that's something that people go, when I give this talk in applied math, that's what they say they want to know next.
Yes, one question. In your capture time, does the leading term in the asymptotic give you any geometric information other than like volume?
That would be beautiful, is it, if you give it topology or something nice like that, right?
If you did in the Laplacian case, it was just the volume, right?
Yeah, you get the volume. So
is it still the case?
So the rigidity statement is that you get the volume. Maybe the lower order term?
Yeah.
Right, so you got to compute the lower order terms. Right, so it's like a Weyl asymptotic almost.
Yeah.
Okay, so maybe we'll stop here. So thanks again.